everybody. Today, we must move a small but very important step towards tensor calculus. Up to now, we discussed tensor algebra. Okay, so we have studied the algebraic structure of tensors, and we defined everything about this kind of algebra, which is based on the concept of vector space and its dual. Okay, during the lectures, we will come back to tensor algebra, but I hope that I gave you the basic ideas. I hope I gave you the basic ideas of it, and now you should have the fundamental concepts for understanding this powerful notation, how it has been built, the basic principle, and the basic structure. Now we will, but this is a much more difficult subject, so we will deal it in a different way. We will not prove everything or nearly everything as we did now, up to now. We will start discussing about tensor calculus. So we are calculating, roughly speaking, we are calculating integrals and derivatives of tensor fields. So let us discuss a little bit this point. We already, without knowing very much about tensor algebra, we said, okay, I introduce a basis in the reference configuration. Every point, every material point in the reference configuration is labeled with capital X, the position of the material point in the reference configuration. So capital X is the position of a material particle in the reference configuration. And sometimes, for remembering this, I place the lower index P. Why? Because the same lower index labels small xp the position of P in the actual configuration. Okay. So key, the placement field, maps positions in the reference configuration into the position in the actual configuration. In the actual configuration, we have chosen a basis small e1, small e2, small e3, of course also an origin. So capital XP is represented by x1p, x2p, x3p capital, and xp small p is represented by x1p small, x2 small, x3 small. Okay, so the placement maps positions in the reference configuration into positions in the actual configuration. Then we did it so many times that you should be even bored about this. We said, let us calculate the Taylor expansion. Now I will write it in a vectorial notation. So in the neighborhood of a certain x0, so close to x0, we zoom the drawing. So you have x0, and here you have the diameter epsilon. So the epsilon is small. So this is enlarging here. Okay. In this zoomed region, the placement of every point capital X is given via a Taylor expansion truncated at the first order. So here you have d key over d capital X calculated in x0. This is one possible notation, x minus x0 plus infinitesimals. An alternative notation which we have used was nabla key calculated in x0, x minus x0. Another notation common in continuum mechanics is f of x0, x minus x0. This notation is reminiscent of the Jacobian, the matrix, the remark that this is a matrix because this is a linear map, but we are representing it in the basis small e1 and capital E1, E2, E3, and capital EI. So this linear map here we are underlining the fact that we are dealing with a linear map. Here we introduce nabla notation, where the derivatives are represented with this symbol, and this is reminiscent of the structure of the matrix representing the Jacobian for the three functions key1, key2, and key3, which are function of capital X1 up, capital X1, capital X2, capital X3, and so on. So we have all partial derivatives of these three functions. Okay, so what we have done, we have introduced a field, capital F of capital X is a function associating to every capital X the linear map nabla F, nabla key. Okay. So what we have? We have a field of tensors. In every point, capital X, we consider a tensor. Okay. So, how did we get this tensor? calculating the partial derivative of the functions ki. And we have called this FIA. Okay. Now, if you are somebody who hears me carefully, you immediately should ask yourself why you are systematically placing the index I at the top and the index A at the bottom. Why you did it all the times, even when you didn't say us the reasons for using the upper and lower index notation. So in order to remember what I wanted to do this morning, I wrote few lines and we will enlarge these lines now. Okay, so let us change the coordinates. Okay, so if we move from the coordinates capital X A prime into the coordinates capital XB, we have the contravariant transformation. And if we move from XB to XA prime, I wrote it wrong. Okay, so let us. Okay, so we are moving from EI into E capital A into E capital B prime. Okay. And the matrix transforming EB prime is equal to T A B prime EA. Okay. Now, if you move from B without index, the components here, okay, into the components, the new components in the new basis. So these are the components in this basis, and these are the components in this basis. You have, as we have seen in detail, contravariant transformation. Okay? And in fact, you remark that the index with the prime is at the top, not at the bottom. So in our notation, this is representing the inverse matrix. Okay? If you remember, we made these calculations. So moving from X prime, XA prime into XA prime into XB requires a covariant transformation. Okay? Because you must go from XA prime into XB. Okay. So when you calculate this partial derivative, you apply the chain rule. So the derivative with respect to the new variable a prime, you can calculate summing up over the index b of the old system of coordinates, and each of the old coordinates you derive with respect to a prime. So this equality is related to the chain rule. Okay. Then you are left with this partial derivative and d capital XB over dx a prime. You must calculate the partial derivative of this linear function. Okay. And dxb capital XB with respect to capital X a prime, it is exactly TB a prime. So we discovered that passing from the old partial derivatives to the new partial derivatives, you need the covariant transformation. So nabla is a covector because it is transforming like a covector. Now, maybe you understand the reason, one of the reasons for which the notation upper lower index is so consistent. Because you have a contravariant variable, up index. You calculate the partial derivative with respect to the contravariant component, and what you get, a low index covariant. Okay. So when you write this symbol, you are strongly suggested to use the up and low index for covariant and contravariant components. Okay. Okay, be careful and check alone, repeat this reasoning here and be persuaded that what I'm telling you is correct. Okay? There is an abuse of notation because depending on where you have the prime, you are considering a matrix or its inverse. Okay? So when you have the prime down, you have the covariant transformation. When you write the prime up, to be precise, one should write this. Because this is the contravariant transformation. Okay? So maybe we can organize one lecture. I will ask to Alessandro to organize one lecture in which he will repeat once more these things to you, obliging you to intervene in the discussion so that we are sure that you are catching these simple points. You know, I have ready the lecture notes where we have written everything with all appropriate notations. And to be honest, we got a good result, but heavy. The notation becomes very soon really heavy. So for writing a single thing, you need a lot of time. While with this notation, essentially due to Einstein, a gossip says that this notation is due to the first wife of Einstein, Mileva. She was also a student in physics with Einstein. Then she wanted to have children, or she married Einstein, and she was obliged to look only after children. And so when Einstein needed to develop the calculations, the basic calculations of general relativity, she did everything. She made the calculations, and probably this team invented these shortcuts, because Levi-Civita was using these ideas mainly, but without all these shortcuts I am using now with you. So now let's go back to our FIA. It is a tensor. We have proven now that it is a tensor. One time contravariant in the basis small ei in the space V small, and one time covariant in capital EA in the space V big. Okay. So we can talk about a linear map F, which is the mathematical dress of a tensor, mapping the segment of material particle x minus x0 into the segment of displacement of positions small x minus small x0. And so we can write this forgetting the components. Because you change the basis, and to the same vector x minus x0, you are associating the same vector small x minus small x0. As we said when we have spoken about tensoriality criteria. Okay. Very well. Now we stop for a while the analysis of tensorial algebra and tensorial calculus, and we go back to our principle of minimum energy. Okay. So we change drastically our point of view, because up to now we have described kinematics. So what we did, we have invented models for describing the state of the system. So I think that this morning we should, I think that very often students following my lectures, I mean, the less polite, or maybe those who are more polemical, somebody of them many years ago told me that I am schizophrenical. They remarked that I am switching quickly from very rigorous mathematics. I'm telling you in very small detail how an index is contravariant and covariant. I am even telling you something about logics. So I'm explaining you the contra-nominal implication equivalent to the direct implication. And then in few minutes, I switch to what some of my students called, in an insulting way, philosophy. Actually, it is true. This is philosophy. But what we are telling you now, what I want to describe you, is a part of philosophy of science. So, in a sense, the theory, or the tentative theory, because there is not a well-established theory, for constructing theories. So, what is a theory? A theory tells you how to build. Thermodynamics is a theory. What is telling you thermodynamics? How can I build engines which are energetically efficient? Structural mechanics is a theory. How to build a building which is not collapsing while I'm building it, and eventually is not collapsing when an earthquake arrives. Another theory, aeronautics. How can I build an airplane which is landing, taking off without being broken, and arrives without killing passengers? So a theory usually has as object of its discussion some physical phenomena. Okay. Linear algebra is a theory talking about other theories. So describing other theories. Why? Try to think about this. I gave you a definition of vector space with an inner product. I told you that a vector space is a set. Did I tell you which set? No. In this set, you have a sum. You take two vectors and you sum them up, and you got another vector. A product with a real number. Then I told you that there is the zero vector, the opposite vector. I gave you the fundamental rules of algebra of vectors. And then finally, I added a bilinear symmetric non-singular map from the space VB into real numbers. And then we studied what we can do with this structure. In particular, we studied the case when the dimension of VB is smaller than plus infinity. It is a natural number, a finite natural number. So I developed the theory of vector spaces. This theory is telling you how to study, how to this theory is applied to what? To the study of R3. So the vector space theory is talking about some phenomena which are not occurring in real world. The theory of vector spaces is talking about how R3 is behaving, or how Pn, the set of polynomials of order n, are working, or how the set of displacements, so the arrows in the space, are working, or if you skip the requirement that the dimension is finite, so these are finite dimensional spaces, the theory of vector spaces is telling you what the set of continuous functions defined in an interval is behaving, or how the set of k times differentiable functions in the interval AB are behaving. These are all particular examples of vector spaces. Okay. So the theory of vector spaces is, if you like to use an elegant Greek way, is a meta theory. Meta in Greek means beyond. Okay. The theory of vector spaces gathers all common properties of many lower rank theories and synthesizes what these theories have in common. Okay. So scientists are building meta theories over meta theories. So you mathematicians actually are building sequences of meta theories, more and more abstract. So you don't understand immediately what linear algebra is dealing with, because it is a meta theory whose object, whose phenomenology is not real phenomena occurring in real world, but the phenomenology, so the facts that we want to explain, are other mathematical theories. Okay. Now the situation is made even more complicated if we want to learn some rules for building theories. So let us call them physical theories. So what I want to say, I have a set of phenomena. Look, phenomenon is a Greek word. I'm sure that in every language, included Turkish, Georgian, Japanese, I believe also Chinese, you use phenomenon, the same word, for meaning facts observed in the real world. This expression is in English more or less equivalent of facts observed in the real world. Now, when we have discussed about linear algebra, we didn't talk about facts observed in the real world, but in the world of mathematical truths. So the phenomena we discussed here concerned some mathematical true statements, and we observed these facts, and then we invented a theory for organizing these facts. So when we talk about a theory, we in general refer to phenomena in the world of mathematical truths. When we talk about physical theories, we talk about phenomena which occur in the real world around us. Now, I stop talking about these things quickly, because otherwise we could go too far, because one could tell me what it means existing in the real world. You know, there is a part of philosophy invented by Greeks called ontology. In Greek, ontology means the science of being. Okay, we accept that we can agree about a set of facts which are observed by everybody. So there are facts. We are really talking now. The sun is shining outside. I mean, there is a set of basic facts in the real world, and we can agree about their existence. Okay? You know, some Jesuits discussed that what Galileo was observing was in his imagination. So when he went and used the telescope and he showed them the spots in the sun, they said, it is not the sun which is corrupted. It is your telescope which is not working. It is your eye which is not seeing well. It is your brain who believes to see the spots. Okay? So ontology is very important in our discussion. However, we close this, which is too much philosophical. Maybe we will do something at the end of this course. we agree that everybody in our classroom accepts the same set of real facts about the world. So everybody here agrees about what is existing in the real world. Or if you like, as a modern philosopher of science said, we are all crazy in the same way, so that we all believe in the same reality. Okay. Okay, so we have a set of phenomena. The literal translation of phenomenon from Greek is what appears. So remark that the Greek is very sophisticated. They didn't say what exists. They choose what appears. So actually, we don't mind about what is really existing. We simply mind what we see. Okay. Okay, so we have a set of phenomena, and then we want to forecast future phenomena. So this was the look, we more or less belong to the same culture, so we should not discuss about this, because whatever say Turkish people, they belong to the Mediterranean culture. You are quarreling periodically since Xerxes and Darius with Greeks. Turkish Persians were defeated in Salamina. Now you want to conquer another one. You are good friends fighting at the borders. So you belong to the Greek culture. Georgians are even more Greek. You know, they speak English with a strong Greek accent. So whatever they say, they have the same tradition. I am from South Italy, Magna Graecia. So we all agree that Hellenistic philosophers invented science in the form which I am describing you now. So what is the idea of Hellenistic physicists? You have the real world. So just not forgetting what we are doing now, imagine we have the real object, which I'm drawing here. This is a beam, a fat beam, clamped in a wall. And with the drawing of Galileo, we have a big stone connected at its extremity. Or you have a pipe and you have an incoming amount of water and an outgoing amount of water from this pipe, and you observe the flow lines of this fluid inside. Or I want to do this quick example for you. The appearances you have is the motion of celestial bodies in our sky. You know, recently I'm playing with a modern camera, and I wanted to shoot a picture during the night to see the landscape from my mother's house. As there is not enough light, I needed to expose the sensitive surface of the camera for 40 seconds. And what is very astonishing is that I have seen the trace of the boats moving in the sea. But I have also seen the traces of some stars in the sky, and the moon moved. So I had an half moon, and I've seen nearly a full moon because the half moon moved in this period. So the light was filling a bigger. So the appearances, the real world phenomena I'm talking about is the movements of stars and planets as observed from the Earth. Okay. Now, what are suggesting Hellenistic scientists? Let us introduce mathematical models. These mathematical models must give a description of real-world phenomena and must forecast what will happen in the real world before the phenomenon occurs. So I want to start with the historical example. Of course, to develop fully the theory could be a nightmare. I mean, we could need another course. I hope that you studied, in physics in the Russian school from where Georgian students are coming, and also partly Turkish. In the Italian school, in the French school, in the past, you couldn't become an engineer if you did not study the motion, the basic ideas of motion of planets. So there was a big debate. So what I'm telling you was studied in physics 1, first year, even at the very beginning. So there was a big debate about in Hellenistic science, in Middle Age science, in Renaissance science, for inventing a model for describing the movement of stars. So I try to compress this in half an hour. So it will be a brutal resume of complicated ideas. We need simplifying assumption. Which kind of simplifying assumptions? The moon is big. We see that it is not a small point. So we model the motion of the moon by introducing the position of the moon as a function of time. So in a sense, we say we are happy, we are satisfied by knowing where the barycenter of the moon is located. This is a simplifying assumption. Is our theory effective in this case? We will see at the end. So what I want to underline is that I cannot know at the beginning if the assumptions, you can call them conjectures also, are good enough to describe the phenomena to which we are interested. So in general, when describing for you a theory, I cannot tell you when I am formulating one of these simplifying assumptions, why this simplifying assumption is good. The only thing I can tell you is, believe me, in the books, all these theories are developed. We deduce some predictions. These predictions are experimentally verified. We can judge the conjectures only at the end of a long procedure. So when somebody tells you that it is experimentally verified that my assumption is true, they are, in a sense, simplifying too much a very long reasoning. Okay, so let's go ahead. We introduce x of s, the position of the barycenter of the sun. Then for every planet pi, we introduce the position of the planet as a function of time. And then following the ideas of Greeks, you know, they did manage to understand that the solar system is made by a sun and planets around it, and that the other stars were far. So there are some stars which are very far, and these stars are more or less after a lot of reasonings, they understood that these stars are always in the same position. Okay, but you know, this required a lot of reasonings. Why? Because let us see the appearances. So the phenomena observed. The phenomena observed are: the sun is arriving from east and then falling down on west. Okay. The moon is appearing somewhere related to east and going down somewhere related to west, but not exactly there. And it is doing strange trajectories compared with the sun. Moreover, the moon doesn't appear always with the same light. So sometimes the shadow of the Earth is projected on the moon. So while nothing is obscuring the sun, except clouds, but we see that they are close, the moon has not its own light. So the distinction between the sun and the planets is that the planets do not have their own light, while the sun has its own light, so it is producing light. Okay. Then, if you see Mercury, you see that the motion of Mercury is doing something like that with respect to the Earth. What is called retrogradus motion. It goes back, forth, back and forth. So it is rather strange what is happening. Okay. So after a lot of reasonings, Aristarchus of Samio, I should know how this is said in English, I should check. Aristarchus invented a model with these ingredients. He assumed that the sun is in the middle, that every planet is traveling around the sun. He approximated this trajectory with a sphere, with a circumference. He placed all planets in the order, in the right order. How? We don't mind. This was a conjecture. He conjectured a certain order of the planets and then said the Earth is revolving around its axis. So for making things more complicated, we have that the Earth is a sphere turning around itself. So somebody among you could say, you did assume that the position of the Earth is given by only where its barycenter is. So you are not describing the rotation of the Earth around its axis, because at one point it's not rotating. So you need the rigid body motion, which we described, if you remember, at the beginning of our lectures. So he assumed that for instance, this observed Mercury movement is the effect of the rotation of the Earth, the rotation of Mercury around the sun. Mercury is inside an inner circumference. So the Earth is running, but not enough, quickly enough. So Mercury is running ahead of it for a while. Then the Earth is rotating around itself. So the apparent motion of Mercury, as seen by an observer on the Earth, is the effect of the motion of the Earth around the sun, the motion of Mercury around the sun, and the rotation of the Earth around its axis. The apparent motion of the sun is the effect of the rotation of the Earth around its axis, and you have a moon which also rotates around the Earth, and it is much closer. By the way, Hellenistic scientists could measure the distance between the sun and the Earth, and the moon and the Earth rather carefully with astronomical measurements. So they could even estimate the radius of the Earth. Eratosthenes did it very carefully. So you describe the apparent motion of stars and planets via a simple of hypotheses. I want to underline for you that you assume that every planet is a point, which is clearly not true. However, you claim that you can describe the motion of a planet knowing where its barycenter is. So you assume that the interaction between planets, between planet and the sun, can be fully described knowing only where its barycenter, their barycenter is. So this is a simplifying assumption, okay? Then you assume some basic assumptions. We don't know exactly, because we have lost the books, we don't know exactly what Eratosthenes, Hipparchus, Aristarchus knew, developed the theory. We know only their results, but at the end, Marcellus, the Roman conqueror of Syracuse, found in Syracuse a big analog computer. This big computer had the sun in the center, then an arm, and it was built Venus, then another arm and Mercury, and all known planets there. There was a set of gears. So there was also the Earth. So somebody could turn the wheel, the gear, an handle, and all planets were moving around the sun, following the real relative position. And what is very clever, as it is described in an historical book written by a Latin writer, you could either block the sun and see the motion of planets around the sun, or you could block the Earth and see the apparent motion of planets and the sun around the Earth. So you could forecast the position of planets using this analog computer and the simplified model of the motion of planets. Now you understand why the word forecasting has been linked to stars and why astrology pretends to be a science forecasting the future of human beings. Because Greeks were so proud of the fact that they could forecast future simply with their mathematical calculations that everybody accepted the idea that forecasting is possible. Then mathematics was lost because people did not study mathematics. This is another story we will discuss maybe another time. Okay, so true science was lost and it was replaced by astrology. And you know, there is a famous Italian expert of astrology who in January 2020 said, this year is the best one for traveling. You see? So these astrologists are very, very capable to predict everything. Okay. So in the popular vision about life, stars are linked to forecasting, but this link has been corrupted. The true historical fact is the following. The first theory which organized phenomena in such a way that you can forecast eclipses, the position of the planets with respect to the Earth, as seen in the Earth, okay? This theory probably has been the first one ever developed by human beings. I want to conclude this now. Please don't believe that, you know, arrived at this moment, as many students, you know, in Rome, I was teaching in Rome many years. In Rome, students are extremely impolite. You know, students in Rome are very, the spirit of people from Rome is to be very impolite. So a group of them, after having said to me that in modern engineering, linear algebra is useless, and this is ridiculous. There is every code is based on linear algebra. Computers are working because of linear algebra. So this is a simply stupid statement. They also told me that I had a psychological problem. I wanted to be a physicist and I could get only a position in engineering. So I was boring students with the motion of planets. Okay. First of all, maybe you know that there are groups of persons who believe that the Earth is flat. Go in internet and you will find websites. Recently, 2 Italians took a boat and went south in the Mediterranean Sea because they believed that the Earth was ending there. So they risked to die looking for the end of the Earth. Okay, so there is a first reason for which engineers should know. It is general culture. But also there is another reason. We will need to build a mathematical model for beams and structures. One beam is an object which is much more complicated than the solar system. And you need a mathematical model which is more complicated. And you need simplifying assumptions. So if you have understood without, you know, anybody who has any idea of what turbulence is should know that to describe a turbulent motion of a fluid is simply a nightmare. Nobody knows how to model turbulent motion. So we know how to forecast the position of Venus in the sky, but we do not know what is happening in our sink. If you open your sink and you have a turbulent motion originated in it, there is no sound mathematical theory for describing what is happening there. So the discussion about model theory. So the theory, the meta theory, which is teaching us how to build models, is very important for engineers, because there are many phenomena which are not yet described. Okay. And unfortunately, while I can teach you everything about covariant and covariant components, model theory is not as developed as linear algebra. So I cannot teach rules. There are no rules. I am optimistic, so I will add yet. Teaching us how to build theories. Okay. So what can I do for helping you and myself? We can see how theories were invented, to try to learn how to invent new theories, how old theories were invented, to try to learn how to invent new theories. We are a little bit like the pupils of Michelangelo. You can only enter the shop of Michelangelo and see how he's building statues or painting frescoes. You can try only to see how our maestri learned how to build theories. So to see how the planetary system was invented and how the model for planetary motion was built is very important if we want to build new theories. I have 7 minutes. So I want to tell you that there is no theory for everything. Forget to be able to describe with a theory every phenomenon. You must be happy to describe some part of phenomenology with a theory. Okay. By the way, these things I have written in a chapter of the book of Cambridge University Press, so you can find it. I will give it to you. Okay, I give you the classical example. Okay, we described the motion of the Earth around the Sun and the motion of the Moon around the Earth. And we assumed that the Earth is moving following some rules, okay, and the Moon also, and the planets also. Then, I forgot exactly when, somebody discovered that Mercury is not following the laws of the motion of the other planets. And the problem of forecasting the position of Mercury remained there for many years. Everything else worked. Mercury did not, nobody managed to fit the motion of Mercury inside a mathematical model until Einstein produced relativity equations and calculated the speed of Mercury. So the speed of Mercury is so close, is closer than the other planets' speed to the speed of light, so that you need a relativistic correction for describing in an appropriate way the motion of Mercury. So we know that we cannot describe all the time every aspect of reality using a unique model. Every time when somebody declared, my model explains everything, unfortunately, soon a phenomenon not explained by that theory appeared. So you must intend, you know, if this is the set of phenomena, there is a partition of the set of phenomena. Here you have theory 1. Here you have theory 2. Here you have theory 3, and so on. Some groups, subset of phenomena are described by a theory. But unfortunately, it seems, but nobody knows actually, our experience about meta theories, about the meta theory, so the theory of the theory conjectures that there is no theory of everything. There is a nice book written by a Nobel Prize, I think. This book has a very provocative title. The theory of everything forecasts nothing. It is too general and it cannot be used for forecasting anything. So now what we will need to do in the next lectures, postulating the principle of minimum of energy, we will develop a specific theory, the theory describing the deformation of bodies and the flow of fluids. Okay, so we will need to see this in greater detail. Okay.
Hello, Mr. Francesco.
Yes.
Mr. Francesco, you know that when something is burning on the earth, for example, in our world, it has his own length, weight, and so on. So I have a question with you. What do you think? It is possible to calculate, for example, weight or diameter newborn earth when it's started. You know that scientists are looking at that it has happened million years ago, and when has happened a big explosion. So I think that, in my opinion, it's really possible to calculate the size of newborn earth, our planet. And what do you think about it?
Sorry, Odar, I really don't understand some of your words. Maybe there is a sound problem. There is a communication problem. So can you repeat slowly?
Okay. Yes, it's maybe about connection. My question is like that. You know that when something starts born on the earth in our planet, it has their own sizes. For example, for human being, It's
you know,
weight
you
and
said
the length.
born.
Can
I
you tell me?
didn't catch your word. When on the earth, you said something. When something is born on the earth?
Yes. It has their own specifications. For example, something like that, weight, height, or something else, length, or something else. And my question is about that. This our planet when it's born billion years ago. We can is it possible to calculate its own specifications, for example, diameter or length, weight, or something else?
Look, you are proposing a challenging problem. I know an expert in this. She's professor in the Second University of Rome. They are working. I think there is a group which is working now. It's 40 years they are working on it. They want to describe the phenomenon of aggregation of the interstellar powder to form a new planet.
Yes.
And my dear friend, continuum mechanics is playing a role in this modeling effort. So, my dear friend, you are addressing to a very difficult problem. However, there is somebody trying to solve it, even if there is not yet a solution. So you have, I think that you, with your question, you are perfectly centering the spirit of what I'm telling you now. So there are so many challenges around us that everybody among you must learn how a new theory is born. Because the hope is that some of you will need to work to the building of a new theory. See?
Yes, I have my own theorem about this, and it looks so simple. But when you going deep, it's getting harder, and I am working on it at the moment. And when we will be will be able to meet each other, we can talk about and discuss.
Absolutely. But I think that you need to learn some continuum mechanics. You know, these people are modeling even galaxies.
Yes.
With a version of continuum mechanics. So the whole galaxy is a deformable body, and they are writing the equation of motion of a galaxy using an equation of motion very similar to the one written by Piola. You know, the range of application of these theories is not clear. This is also something we will discuss. Okay, Odar, I am very happy that I managed to have your eyes brightening after.
Thank you.
Okay, but today this is non-technical. We will go back immediately to technicalities, but I needed to tell this for explaining you why we need assumptions and to explain you in detail the specific assumption we use in continuum mechanics. Okay?
Okay.
Okay. So I think next lecture is in 2 days, right?
Yes.
Okay, so we switch off the recording and